上课啊。好，还是提醒同学啊，如果你看影片或在家，还是记得要去刷 QR code 啊，因为如果你没有刷 QR code，就是学校还是会寄通知给我，那我会收到很多通知，所以Web 上面有 QR code 哈，那记得去硕士班不要扫错哈，硕士班跟学士班的 QR code 是不一样的。Okay, here's a reminder, okay? Make sure you scan the QR code, okay, before you take this class, okay? So it's right here. Make sure you scan the right QR code. There are two QR codes, one for undergraduate student, the other for graduate students, okay? So make sure you scan the code before you start the video or you start the class. Okay, last week we introduced some basic idea of deep learning, so including several things like what is deep learning and how do we map deep learning neural networks to, for example, regression. Okay, and there are several things you have to deal with when you design your own deep learning model, like how do you stack your different layers to build a model. Okay, there are several different layers, so we'll introduce some others today. And to build a model, okay, basically it's like an art. Okay, so it's a little bit difficult, but we have a lot of examples to help you to understand what is the functionality of each layer and how they affect your result, which is your target Y. Okay, and we introduce several activation functions. Okay, and there are linear functions that help you to map input data to output layer. Okay, by using a non-linear way, because we believe that some relationship in the real world is non-linear. Okay, so different activation functions, and of course loss functions. Well, several loss functions can be chosen. For example, gross entropy, for example, MSE and AE. However, we rarely use some other functions because for regression, okay, MSE is good enough for us to evaluate how close your model and between your model and the your target Y. Okay, and of course for classification application, you also usually we use cross entropy, okay, or binary cross entropy to match your output result and the actual Y. Okay, and also we do some concept of optimizer. Okay, basically there are some variation of gradient descent. Okay, they're trying to find the lowest point of on the surface, or your MSE surface or your loss function surface. Try to figure out what weight, okay, what kind of weight can make your loss function to be very, very low. Okay, minimize the function. However, there's several concepts, for example, momentum or some adaptive learning rate. Okay, they are very nice concept to increase the speed to find the lowest those function value. However, we really change it. Okay, of course you can select different optimization functions. You can choose different learning rate to see if it truly increase the number of steps, the number of epoch to find those data points. However, usually we use some very basic or some very popular optimization functions such as ABA or Adam or some other optimizer functions. Okay, so today we'll try to explain what is convolution. Okay, it's an important concept of layers. Okay, so let's go back to slide. Okay, I'll try to explain it. Okay, I will continue this slide. Okay, so some of the example will I will use some old examples. Okay, so we started from this one. Okay, this is a very basic neural network. Okay, that's one input layer, several inputs. Okay, from x1 to xn, and we have one hidden layer. Okay, have two neurons and one output y. Okay, there's several weights on it, and for the red circles, okay, those are activation functions. Okay, those activation functions help you to map the nonlinear data. Okay, from the left hand side to the right hand side. Okay, that's a very basic neural network. Okay, so we would like to introduce what is convolution. Okay, basically it's a layer. What is convolution layer? Okay, take a look at this figure. Okay, for example, for H1, which is the hidden layer, one of the neuron in the hidden layer. Okay, it receives information from the previous layer, which is x1 to xn. Okay, all of the information will times an individual weight, which is w11, w21, w31, so on and so forth. So those we will H1, okay, which is the neuron. Neuron will consider, okay, different weights on different informations and sum up them, okay, to make to integrate those information, okay, and pass through A, which is an activation function, right? So H1 has its own, as a perspective, okay, to view those data. Okay, that is the H1. Okay, but what is convolution layer right here? So basically, okay, we write it in this way. For example, if we have 6 neuron, okay, at input layer, okay, and of course, and here we have 2 neurons, which is H1 and H2, and again we have 1 output layer. Okay, the concept of convolution layer is that sometimes, okay, as I say, H1 has a point of view to look into the data provided by x1 to, for example, x1 to x6. Okay, but sometimes we wish H1 only consider part of the data from the previous layer. Okay, so we would like ask H1 only consider part of the data. For example, only 3. For example, that it is just an example. Okay, only let's take it in this way. Okay, we use 3 hidden layer, which is for convenient. Okay, for example, we only ask H1 to consider 4 consecutive data from the previous layer. For example, if H1 only consider the first 4 information, and for H2 it only consider the next consecutive 4 information from the previous layer, like this, and for H3 again the next 4, so it should be like this one. If there's some information, okay, those information are locally meaningful. Locally means which I mean is it's related to the position that in the layer in the neurons. Okay, so sometimes we believe some information is only meaningful in locally. Okay, for example, 4 consecutive layers. However, before we do this, make sure you understand one thing. When we design our neural network, at the first place we have table, right? So we have several different samples, and with x1, something like that, right? When we design this table, usually, I say usually we do not arrange those features x1 to x6 in some sequence, in some meaningful sequence. You can put your height in x1 or you can put your height in x4. So at the first place, okay, the sequence of how did you arrange your features from x1 to x6? That is, we don't do any restriction. We do not have any restriction how you put your features in this table. So basically, x1 might not, okay, I say might not related to x2. That's independent variables, independent features. Okay. However, for some special applications, okay, such as sequence application, time series application, and the most important application, which is images. Okay, so sometimes when we would like to analyze an image, okay, usually I say usually we view it in this way. For example, okay, that is an image. Okay, so each block right here is a pixel. So it is so we have 20 pixels in this image, and then for each pixel, okay, of course there are several different colors, okay, several different patterns, okay, several different for example, like this. And of course, there are some white pixels or black pixels, something like that. Okay. Sometimes when we analyze input data, which the input features, okay, which is related to its neighbors, something like that. So usually when we analyze images, okay, maybe we will name it as x1, and that is x2, that is x3, x4. Okay, of course picture is a two-dimension data, so usually that is x5, right, x6. Of course you can name it in a more appropriate way. For example, you name it x1 as x11, make it two-dimensionally. Okay, so of course, okay, you can name it in this way. So for less very small picture, it has 20 pixels, and we can use 20 features to describe this image. And for each pixel, okay, you can use some numbers. For example, from 0 to, for example, you can use RGB. It is a way to describe color. Okay, there are 3 numbers from 0 to 255. Okay, it has 3 different colors to describe the color in a pixel. Okay, I believe we learned it in some computer basic concept course. Okay, so basically you can use these numbers, use these features, okay, to describe a picture by using a row of data. Okay, that is one of the ways to describe images. And in this case, usually we believe that the colors of a pixel and its neighbors means, for example, this specific pixel, okay, which is in green, right? We believe if this image is meaningful, for example, it is a dog, it's a ball, it is a cat, it is someone, okay, in this figure, in this picture, okay, the color right here should be related to the color or it's related to this center color. Okay, so the neighbors has meanings because they might have similar colors, they might have similar shape or something like that. So before you use convolution, okay? Before you use convolution, make sure your input data, okay, it has certain characteristics, something like the colors, okay, and its neighbors, okay, which for example x, x3, okay, and its neighbors x2, x4, and x1, they are related. Okay, if you believe your data has such kind of characteristics, then you can use convolution to describe such kind of data. For neuron H1, you don't have to analyze all the entire images, right? You don't have to do that, because if you want to analyze some local information and you believe they are related, then you can use convolution such as H1. But there's an important thing that you believe, okay, neighbors features or neighbors pixels are related. However, you don't know what exact the positions, which means is that left hand side or right hand side, or at the top of this image or at the bottom of this image. You don't know where it is. So basically you can use a convolution like this. H1, which is a neuron only focus on the first few features, first few pixels. Okay, try to analyze the input data. So of course we have weights, like so I write in this way: W, okay, just 1 W21 31 41. Of course H2 has its own weights like this. And next, something like that. Okay, and most important of things is that of course those weights can be different. The green weight, the blue weight, the purple weight can be different. But for convenience, okay, of course you can design a neural network like this, and you have different weights for different neurons. But for the libraries, okay, the libraries provided by Google, by TensorFlow, by Keras, by those packages, okay. When you use convolution neural networks, okay, you want to design a layer like this. Usually, okay, their weights are the same, which means W11 equals to W22, W33, something like that. It is just one of the ways to represent that the convolution layer, but it is not conceptually. I say conceptually, it is not necessary to do so. But most of the libraries, okay, they do so. So the green, blue, and purple weights, they are identical. So when you train this model, for example, of course we have this one. We have another weight right here, and maybe we have a softmax layer right here, and of course we do have activation function if you like to do so. Okay, so basically they look like the same. They're the same. Okay, as the left hand side. The right hand side, if you choose the convolution layer, it just looks like this. Okay, and in practical, okay, blue, green, and purple weights are the same. And the other thing is like, in order to make the model look simpler, okay, in practice, okay, there is a weight right here for the rest of all the connections between the input layer and hidden layer, but they will set this weight to 0, and they will not participate with the partial differentiation. But conceptually, you can see that this weight does not exist. Okay, but actually, when we compute the partial differentiation, those are weight with 0 values. But you don't have to you don't have really to manipulate things. Okay, if you apply the neural network convolution neural network, it looks like this. Okay, so let's take a look at some other things like convolution layer. If you Google convolution neural network, okay, usually they will draw a figure like this. Okay, something like that. Okay, that is a original image. Okay, and here, for example, like this. Because it is a 2D image, right? So we draw it at like this. Okay, so when I draw, okay, the convolution layer, usually, okay, they say that, okay, you create a small image like this, a small square, small pixel like this. That is called kernel. Okay, or sometimes it has another name called filter. Okay, so that is at this moment. Okay, you only focus on the first you only focus on x1, x2, x6, and x7. Okay, and that is the first area you focus on. Okay, and for the next step, they will try to move this kernel, okay, or this filter to the right hand side, or to the from the left to the right, or from the top to the bottom. Okay, so next one is maybe we move the kernel like this, so to this way. Okay, so at this moment you focus on x2, x3, x7, and x8 because they are neighbors, right? So basically, when you try to do such kind of 2D convolution, okay, you can simply say like, okay, I have several input like this, and the first neuron right here, it focuses on 1, 2, 6, 7, right? So 1, 2, 6, 7, which is the green. Which is the green. 1, 2, 6, 7. And for the next neuron right here, it focuses on the purple ones. So that is 2, 3, 6, and 8. So basically, if we look at the input data, and it is a 2D, it is a 2D data, okay, two-dimensional data. Usually, okay, the relationship like this, and of course, you have a lot of different neurons at the second layer, at the convolution layer. It focuses on different area, okay, and the weight right here, okay, of course, the weight right here, they share the weight, they share those weights. Those 4 weights, okay, which we usually describe it as the size of the kernel is 2 by 2. So we have 4 weights right here. Okay, so we continually move. Okay, we use another color. We continually move the kernel through the entire 2D images. Right? So at the end of the first row will be 4, 5, 9, and 10. And for the next step, it should be like this. We'll go back to the row. Focus on 6, 7, 11, 12, and so on and so forth. At the end, it should be this one. Okay, so we can move the kernel from the left hand side to the right, and from the top to the bottom to describe how the original data related to the how local information of the original data can be extracted by the kernel, and we only consider the information in the neuron and we pass the data to the convolution layer. And of course, there should be some other layers behind the convolution layer, and we can make a decision how do we deal with the data received from the local information of the original to the data. Okay, so and so on and so forth. Okay, so basically, if you use TensorFlow or Keras or PyTorch, those libraries to create a convolution layer, okay, there are several things you need to set. For example, what is the size of your kernel? For example, right here is 2 by 2, right? From the above example right here, from the above example right here, we can view it as an 1D, one-dimensional data, and I consider only 4 neighbors, 4 consecutive features. Okay, so my kernel size is 1 by 4, for example, right? Of course, your kernel can be larger, like 3 by 3, 4 by 4, 7 by 7, something like that, or even you can design a convolution, a kernel which is not which is 2 by 3, 1 by 10, 2 by 5, something like that. Okay, that is one of the parameter you have to set if you want to use this. So one is the kernel size. Right here is 2 by 2, for example. The second thing you have to consider is we'll take one step to the next neuron. Okay, so right and down. Okay, overlap or not? Oh, you say overlap or not. Take this example, okay? The green one is x1, x2, x6, x7, right? But the next one is x2, x3, x7, and x8. But you can ask the convolution layer not to overlap those kernels. So you can do that. X1, X2, X6, X7 is the first neuron, and 3, 4, 9, 8 can be the next one. They are not overlapped. You can decide. You can choose to decide. Okay? And of course, when you go to right here, okay, 4, 5, 9, and 10. The next row is start from X6 or start from X11. It depends on your decision. Okay, it depends on what kind of local information you would like to extract from the original layer. So I have to decide these things. Okay. Third, okay, is called walk. Okay, you can walk from the left hand side to the right hand side, right? So how far away you want to walk? Okay, actually, okay, they're related. Okay, actually, you can shift. Okay, what is it? Shift. From X1, maybe you can shift to X3 or even X4 or X5. You can shift your kernel every time in different, we call stride. OK， 就是跨步了哈，我们中文翻译成跨步。你可以决定你的跨步要是多少啊，你可以往右跨1步、跨2步、跨3步，这都可以的啊，这个是你自己决定的。OK。The other one is called padding. Okay, so here's an example. The original size, okay, the original size is, for example, is 5, right? You have 5 columns in the original size, okay? After that, okay, for example, x1, x2 is a kernel, the kernel size is 2 by 2. Maybe you have the 2 by 2 kernel size, right? So after that, and the stride is 1. After that, how many outputs in a row? X1, X2, X6, X, the green is 1, the green, this green kernel will output 1 result, right? The next one is the purple one, right? It will output the result. And next one, maybe the red one, will output the result, right? And the last one, which is the pink one, will output the result. How many result will be output if you take a walk from the left hand side to the right hand side? Actually 4, right? Because our kernel is 2 by 2, so basically we cannot output 5 result, only 4, because we overlap it. The kernel is overlapping. Okay, so sometimes for convenience, okay, we would like to that the output size, okay, which is 4, equals to the original size, which is 5. So you sometimes, okay, again, sometimes we ask the convolution layer to add 1 additional layer, 1 additional column and rows right here, so that when we move those kernels, okay, there will be 1 extra place right here, and this can still output another result, okay. However, the local information only include x5 and x10, and usually when we do such kind of padding, we simply put 0 right here, which means no information. So in this case, we can output 5 for this row, for this walk, okay. And this is the direction from here, and for example, of course, and on the other direction is right here. So originally, we have 30 pixel right here, 30 data right here, right? It is 5 by 6. But after padding, and if our kernel is 2 by 2, okay, after padding, we can still output 5 by 6 result after we do such kind of convolution. This is just for convenience, because we don't want the number of data in each dimension will decrease when you apply convolution layer. So padding is a very commonly used way to keep the size will be the same as the original 2D data. Okay, so sometimes you have to do that. And usually we do this. Okay, but you have to decide what is the kernel size. If you want to overlap those kernel size, or how did you do such kind of a walk? Okay, you have to set all those parameters when you apply those when you use this convolution layer. Okay, by using PyTorch or TensorFlow or any other packages. Okay, so I think that is good enough. Okay, so the next thing I'd like to talk about, what exactly the weight right here. As I mentioned, for the convenience, usually we set all those weight as the same value. Okay, so the green weight, the blue weight, and the purple weight right here, they are the same. But what exactly it means? Okay, so we still use this figure. Okay, so as we know, okay, it's right here, right? The green part is right here. What is the mathematic things we do right here? It is x1 weight 1, for example, weight 1 plus weight 2, x2 plus weight 3, x3. Okay, let's use this example. Okay, that should be the green one should be x, w x6 x6 w7 x7, right? If you use this example, okay, we summation the weight and input value and maybe pass through an activation function, and the result will be the value, input value of hidden neuron 1, right? Okay, so basically you times this weight and the original value. So basically you can view it in this way, okay? And most of the convolution neural network, they explain themselves as this, okay? Here we have x1, x2, x6, and x7, and we make a a green kernel, and we move it gradually from the left-hand side to the right-hand side, top to bottom, right? And the weight, we simply just write the weight right here, right? Sorry. Actually, the calculation is at the right-hand side, right? It's right here, right? Basically, we times this one with this one, this one with this one. It's a very commonly calculation, right? And we summation them, right? So let's take some example. For example, it is an image, okay? The image looks like this. The x1 x. We assume, okay, the image is a black and white image, okay, black and white image, okay. So here is the black pixel, and here is the black pixel, and the rest of the x2 and x7 are white pixels, okay. So usually, the value, okay, if the image looks like this, okay, the left pixel, the left top pixel and the left bottom pixel is black, okay, and usually the value is 0, okay, 0 is black, white is 1, okay. So if we have a weight in the kernel, okay, and we times, okay, so we times, usually not times, we product, okay, we product w weight and the pixel value, which is 0 or 1, because we assume it is a black and white images. What exactly it means? Okay, if the weight, okay, if the weight is something like that, usually, of course, the weight can be any real number, but for example, we can squeeze those real number between 0 and 1. Okay, so let's take this example. If the weight is like this, 0.0, 0.0, 1.0, 1.0. Okay, if I say if, okay, of course it should not look like this. Okay, I say if the images is black and white and it looks like this, okay, left top, left button is black, right top, right button is white, and your weight, okay, look like this. When you times this, the result will be 2, right? It times this with this one, this with this one, this with this one, this with that. So actually, when we talk about convolution on images, the weight right here, okay, what is that? What exactly it? Sorry. What exactly it means? It means I'm trying to find the weight. Okay, I'm trying to find the weight. If the weight, okay, matches the original local information, which is the pixels in this kernel, okay, if that exactly the same, the result, which is the product of the weight and the x, and we summation them, would be largest, right? Take another example. If I have a weight right here, which is 0.5, and the result should be 1.5, right? So it means the weight, if the weight is exactly the same as the original data, after we do the production， after we do the production 啊，就是product 就是成绩嘛，啊，就是向量的成绩嘛。And the value of the output should be larger. Okay, let's take another example, which is the purple example. Okay, if it looks like this, which means the weight and x, they are quite different. So when you do the product and you summation them, okay, and the result will be 0, right? Because you times this with this one, let's use this one, let's use this one, and let's use this one. The product will be 0. So we can view the convolution there as how similar the weight between the local information x1, x2, x6, and x7. So sometimes we have another explanation of this kernel. Okay, the kernel itself has a weight. The weight looks like another two-dimensional image. Of course, it's a 2x2 images, and we are trying to evaluate how close the weight to the original set data. So for next, what else we need to do? Okay, for the next run, okay, which is the purple one, and the purple one is x2, 3, 7, and 8. And as I mentioned before, we product exactly the same weight, which is still weight 1, weight 2, the purple weight. Sorry. I should only use weight, which is good enough. Okay. We have 4 weights, right? Because all the weight, as I mentioned before, all the weight of each neuron is the same, right? So I simply just use 1, 2, and 3, 4 to represent 4 weights in this 2x2 kernel. Okay. So when we do this at the next run, when we shift the kernel from the first x1, x2, 6, 7 to next 1, 2, 3, 7, 8. Okay, this weight, weight 1, 2, 3, 4, they are trying to evaluate how close, how similar their value is. Okay, so if the weight is exactly the same as x1, 2, 6, 7, the output value will be very large. Okay, if the weight, okay, compared with 2, 3, 7, 8, they are totally different, and the output result, for example, which is right here, will be very, very small. So at this moment, okay, let's take a look at this one, this figure. So neuron 1 will be activated because the output value is very high. So no matter you pass it through an activation function or not, the value of H1 will be larger if x1, 2, 6, 7 looks similar to the weight W. So the neuron will receive a lot of information from 1, 2, 6, 7 combined with the weight. And however, if the 2, 3, 7, 8, okay, the information from the previous layer times a product with the exactly same weight, which is the kernel, and H2, the value received by H2 is very, very low, which means 2, 3, 7, 8 looks different from W, which is the weight. So H1, this neuron will be activated because it has a very high value. H2 will not be activated. So that means H1 and H2 has different point of view to different location of the local data. And H1 activated, it says, okay, there is a pattern. Okay, notice the word I use. There is a pattern which I found in X1, X2, X6, and X7. Okay, so I put a very high value, which means the neuron has been activated. And for the neuron 2, okay, it focuses on 2, 3, 7, 8, but the result says, oh, okay, the pattern of weight does not found at 2, 3, 7, and 8. So H2 does not receive such kind of information. So H2 hidden node 2 is not activated. Okay, so that is how convolution layer works. They are trying to find a specific pattern which is described by weights, and then move through the entire data, no matter it is a one-dimensional data or it is a two-dimensional data. Okay, they are trying to figure out if there is a specific pattern has been found in some local area. So that is the functionality of convolution layer. Okay, we stop right here. We'll continue to discuss how it works and how to use it. Okay, so we stop right here. We'll come back in 10 minutes. Okay.